Good day once again, everybody, and we are back together. All right, so we are still continuing on that IEB question paper from 2024 November, and this is courtesy of Naledi, who has asked us to go through this question paper. All right, so please, if you haven't subscribed, make sure you're part of the family. Right, we've already answered questions 1 till 5. And let's go to question number 6. So they say to us, the galvanic cell represented below functions as a standard or at standard conditions. Right. Now, firstly, I want you to notice there we've got oxygen, that's there, and H2O2. So what I normally like doing is just going to our standard reduction potentials table. Okay. And the half reaction that I found that has those two just simply says O2 plus 2H plus 2 electrons. That will give us H2O2. Okay, the standard potential there, okay, is 0.68. Okay, and then for the other one, you've got permanganate ion and manganese 2 plus ion in an acid. So it's MnO4 minus plus 8H plus 5 electrons. And all of this gives us Mn2 plus 4H2O. All right. And its potential is 1.51. Okay. So what I'd like to do, ladies and gents, sorry that I'm just writing it in such a poor manner, right, is try to identify which one is our anode, which one is our cathode. So you'll notice that the anode is always the smaller one of the two. I've got 0.868 and I've got 1.51, right? We know which parties in government, that's the ANC. And in this case, we know that it is giving away houses. Okay, so in this case, how are we going to work through this? So now I know that for the anode, which means this guy here becomes the anode, so we write it in reverse. Okay, right, it's always helpful to do this at first. So which means I'm going to have on the anode side, that's H2O2 becoming O2 plus 2H plus 2 electrons, right? And then you write the anode in reverse, and then the other one I'm going to write exactly as is. That's MnO4 minus plus 8H plus 5 electrons, which will give us Mn2 plus 4H2O. Okay, right, now I want you to note, ladies and gents, that if we're going to write down the net cell reaction, we're going to have to make some gymnastics over there. But let's answer the questions. They say Lizzie suggests that a manganese electrode could be used in half cell Q. Explain why this would not be suitable. Okay, Lizzie, it would be incorrect because that would give us, it would be a completely different cell, right? That means it would change, right? It would change the cell completely. Okay, you could also say that, yeah, if you add a different half cell, right, it would not, or rather the half reaction may not occur, right? So they say to us, identify the cathode in the cell. We've already done so in this case, 1.51, that's the permanganate ion, right? So, but I want you to please note in this case, so we can say it's electrode Q. Okay, that would be the cathode. They say write down the name of the oxidizing agent. Remember, the oxidizing agent is the one that undergoes reduction, and it is definitely going to be this guy. The gain of electrons, MnO4 minus, they set the name, so that's going to be the permanganate ion. Okay, right, and then they say to us write down the equation for the oxidation half reaction. This is where these reactions I was writing earlier come in. So that would simply be H2O2, which will give us O2 plus 2H plus 2 electrons. And then they say the reduction half reaction, that makes it easier. We said that one just remains exactly as is. So you're going to have MnO4 minus plus 8H plus 5 electrons, which gives us Mn2 plus 4H2O. Right, and they say the net ionic cell reaction. So all we need to do, ladies and gents, is to make sure that the number of electrons are equal on both equations. So I've got 2 here, I've got 5 over there. So for the 2, which means I need to multiply that by 5 to get the lowest common multiple. So that's going to be multiplied by 5. That's 5. That's 10. And that's another 10. Okay, we multiply this by 2. Okay, to make 10 electrons. So that will be 2 times 8, that's 16. That's 10. That's 2. And that's 8. Okay, right. So in this case, when we've got anything that is similar on the same side, we're going to add them. Things that are different on either side, okay, or similar on either side, we are going to subtract. Now notice that, subtract with that, we've got hydrogen, H plus, on either side. We've got 16 plus, we've got 10 here. So 16 minus 10, remember, this is on the left hand side and this is on the right hand side. So 16 minus 10 would give us 6. Okay, so let's write down the net cell reaction. That would be 5 H2O2 plus 2 permanganate ions, this guy here, but we know 16 minus that 10 over there would give us 6. And in this case we've got, which will give us 5O2 plus 2Mn2 plus 8H2O. All right, so that is how the cookie crumbles, ladies and gents. That would be the net cell reaction. Okay, right. Now let's go on to the next question. They say calculate the E cell, the reading of on the voltmeter when the switch is open. So remember, all we do is E cell, that's standard cell, that's E cathode minus E anode. And so that would be 1.51 minus, remember, we were given there 0.868. Right. I get 0.83 volts. Okay. Right, now they say when switch S is closed, the reading on the voltmeter decreases. State two ways to minimize this decrease in the reading. Right. So in that case, please remember, what happens in this cell is that, remember, because it's a closed system, there's a lot of internal resistance that takes place in this case. So what you want to do is you want to try and minimize that internal resistance in the cell. So you can use a wider salt bridge. Okay. Or they said we should suggest two. Okay, we can also use a shorter salt bridge just to minimize those losses. Okay, and you can also use bigger electrodes, right? Bigger electrodes. With wide surface area. Okay. Right, and then they give us the next one. They say to us, in a different galvanic cell, half cell Q functions as the cathode. Zach writes the cell notation for the half cell on the right hand side as follows. Okay, so it gives us anode on the right hand side. Whoa, okay, that's a lot of things. They say standard conditions were not required. Identify 3 different errors that Zach made in the format of the cell notation. Right, so let's start here. Okay, the positioning of platinum, okay, should come last. Okay, so that should be last. But look at what he or she did. Oh, that's Zach, so I'm assuming it's a he. Okay, so in this case, he has used, see that between the permanganate and the Mn2+, they don't change phase, so must put a comma. Not, I don't know what this sign is called, right? Between the aqueous substances. All right, so let's go on to the next one. So I think, oh yeah, also just putting those numbers there. Okay, using of the balancing number. We don't need to put that in the cell notation. We can put it in the net cell reaction though. Right, in 6.8, and we go to the next one. They say the electrolyte solution in both half cells needs to be acidified. Okay, give a reason why sulfuric acid and not hydrochloric acid should be used in the half cell Q. Okay, use the standard electrode potential to assist you. Oh my, okay, I'll have to open it in a different document. Let me just see. Okay. All right. Okay. Right. So if you look at your standard potential table, particularly the one that I'm using, Cl is right at the top there, right? So Cl minus will be oxidized, right? Right, and when you look at as opposed to right, so if you use chloride, hydrochloric acid, or hydrogen chloride, in that case, okay, let's see, it will be oxidized by permanganate ion, right? Whereas sulfate ions will not be oxidized. Ladies and gents, we are going to leave this section here, right? Catch us again when we do question number 7 on electrolytic cells, right? And we are almost done with the paper. So please do catch us again on the next one. I'll see you guys next time. Sharp, sharp.